All right, check this out. We're looking at a machine that, at first glance seems ridiculously simple. People even call it a do-nothing machine. But it has this one amazing, almost secret talent. It can draw something that is mathematically perfect.
Just watch it go. The handle spins, you see the sliders just gliding back and forth in their tracks, and a pencil hooked up to the arm traces out this beautiful, smooth curve. It's such a cool contrast, right? The machine itself looks so basic, but the shape it creates is so elegant. So what is it actually drawing? And just how precise is it?
So what do we call this cool little gadget? Well, it actually goes by a few names. You might hear it called Archimedes' trammel, or an ellipsograph, or, like we said, the do-nothing machine. But what it really is this fantastic physical model that shows how super simple rules can generate these complex, absolutely perfect patterns. Okay, so to really get how it pulls off this magic trick, we first need to understand how it's built. It's just a beautiful example of how a few simple parts, working together in a really constrained way, can produce a very, very specific result. So let's take a look under the hood.
It all starts with the base. It's this cross-shaped block with two grooves or rails that are perfectly perpendicular to each other. Now, these tracks are absolutely crucial because they establish the two fundamental rules of the game here. Movement is only allowed along a horizontal axis and a vertical axis. That's it.
Next up, we have these two little sliders. Sometimes they're called shuttles. Each one is made to fit perfectly into one of the tracks. That means one can only go left and right, and the other can only go up and down. They're like two little trains, and each one is stuck on its own separate perpendicular railway. And here's the piece that connects everything, the arm. It's got two pegs underneath that fit right into the sliders, and then a hole at the end to hold a pencil. The distances between those pegs and the pencil hole are totally fixed. And here's a cool little detail. By picking a different hole, you can actually draw all sorts of different ellipses. Now, when you see it all working together, this is where the magic happens. As you turn the arm, those sliders have no choice but to follow their simple rules. One goes up and down, the other goes left and right. And this combined, restricted motion forces the pencil at the end of the arm to follow this incredibly specific, elegant path.
So we can see it draws this really nice oval shape. But this brings up a much more interesting question. We've seen how it works mechanically, but now we need to ask why it makes this specific shape. And to do that, we have to switch languages, from the language of mechanics to the language of mathematics.
So here it is, the million-dollar question. Is the curve that this little toy traces out just a nice ovalish shape? Or is it a mathematically perfect ellipse? You know, the kind you read about in geometry textbooks, with a precise, unchangeable definition. Let's find out. All right, for our first approach, we're going to use pure geometry. We're going to take this physical device and turn it into an abstract diagram. Then we'll use the power of similar triangles and the Pythagorean theorem to see if its motion actually follows the rules of an ellipse. And this just shows that translation perfectly. On the left, there's our trammel, doing its thing. On the right, we've mapped its key points onto a coordinate plane. The sliders become points on the x and y axes, and that pencil tip becomes the point x, y, whose path we want to figure out. So the logic kind of flows like this. First, we just label the pencil tip with coordinates. Then, using some basic geometry, we can actually spot two hidden right triangles inside the diagram that are similar to each other. And because they're similar, we know their sides are proportional. So we set up that proportion, do a little bit of algebra, and see what equation pops out. And there it is. Now don't worry about all the algebra in the middle. The real takeaway is that final line at the bottom. For anyone who's ever studied conic sections, circles, ellipses, parabolas, that equation is unmistakable. It is the standard equation for a perfect ellipse. The geometry checks out.
But is there another way to prove it? Of course there is. That's one of the great things about math. There are often multiple roads to the same truth. So let's try a second proof, this time using trigonometry for what some people might say is an even more elegant solution.
So we're using the same setup again, translating our toy into a diagram. But this time, instead of focusing on the lengths of all the different sides, we're going to define the arm's position using just one variable, the angle it makes with the axis. We'll just call it theta.
This approach is incredibly direct. We can describe the x and y coordinates of that pencil tip using the sine and cosine of that angle, theta. Then, we use one of the most famous identities in all of math, sine squared plus cosine squared equals 1, to get rid of the angle and link x and y together directly.
And would you look at that? We land on the exact same equation.
two totally different mathematical methods, one using triangles, the other using trigonometry, and they both lead to the same undeniable conclusion. The answer is a huge yes. It really does draw a perfect ellipse.
So what have we really just witnessed here? I mean, we started with a simple physical toy. Just some rails, some sliders, and an arm. And by translating its physical motion into the language of math, we ended up with a fundamental theorem of geometry.
And here's the crucial point. This thing isn't just a clever gadget. It's the physical embodiment of a mathematical truth. It proves that the abstract rules of math aren't just ideas in our heads. They are actual principles that physical objects can follow perfectly. It's a way to see and to feel and even to play with a theorem.
And that really gets to the heart of it, doesn't it? These beautiful, powerful mathematical ideas aren't just symbols on a page. They are literally built into the design of the world around us. And sometimes they show up in the most unexpected and delightful places, like this little machine.
Which kind of leaves us with one last thought to chew on. If the precise equation for an ellipse is hiding inside this do-nothing machine, what other huge ideas, what other principles of math and science are just hiding in plain sight, waiting for us to find them in the simple objects we see every day?